radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? So on this particular one, what we're going to do, draw our picture, just like all the other ones. First thing we're going to do, draw the picture. So we have a cone, conical tank is going to be a cone. It's going to come down, going to come down. Okay, and the radius for this thing going out this way is 5, and our height is 10. That's what they gave us. Now we do need to know what our formula is. So volume of a cone is 1/3 pi r squared h. So there's what that is. So we have our picture. We have our formula. Volume equals 1/3 pi r squared h. So V is going to be volume, R is going to be radius, and H is going to be height. So let's go ahead and assign variables. Let's assign our values. So this is step 2, step 4, because step 3 is going to come up here in a minute. So the volume, we really don't need the volume. The dV dt, so the rate the volume is changing, is 9 cubic feet. Oops, cubic feet per minute. The R is the radius. They gave us no information regarding the radius. And H is the value they gave us was 6. And dH dt is what we're looking for. Notice dr dt, they didn't give us anything for dr dt as well. If they give you nothing here and it's not a constant value, you have to approach this thing a little bit differently. Now, for those of you guys going, but what about V? We don't have the volume. As soon as we take the derivative, it's just going to be dV dt. So we don't need the volume. But we do need the radius. That's part of the function. So on this one here, we're going to use proportions. So I'm going to make a line here. I'm going to do a little bit of side work here and there, and this is where I'll put it. We do have proportions, though. Radius to the height. The radius is 5 to 10, or we can claim that the radius to height is 1/2. 5 over 10 can reach to 1/2. Multiply both sides by h, and you have the radius is equal to half the height. So we can just, disclaimer basically, half the height. Okay, so now we have our R value as well. So back over here to the equation we're going to use. V equals 1/3 pi r squared h. However, we're placing the r with half a h. So V equals 1/3 pi 1/2 h, all of this squared, h. So this gives us 1/3 pi, and this gives us 1/4 h squared times h. So in the end, volume is, my denominator is going to be 12, so I'm going to have h cubed pi all over 12. In the end, that's my equation. Step 4, step 5 is getting the derivative. So that's where we're at, step 5. So we're going to get dV dt is equal to 3h squared pi, it's just a constant, dH dt, and don't forget that we're still over 12. Okay, so the derivative of V is just dV dt. When I did the derivative of h cubed, I got 3h squared dH dt. My constant that's h cubed is being multiplied by stays. It doesn't go away. We can reduce this and make this problem a little more suitable to work with. So we have dV dt equals, my 3 and 12 can cancel out, and so I'm left with h squared pi over 4 dH dt. And we're now ready for steps 6 and 7. 6 and 7, which is substitute and solve. So dV dt, so I'm going to just bring this up instead of rewriting it. dV dt, I believe, was 9. Yep. 9 cubic feet per minute equals h. H is 6, so 6 squared pi over 4 dH dt. So this gives us 9 equals 36 pi over 4 dH dt. So this gives us 9 equals 9 pi dH dt. And yes, if you're using a calculator, you could have just thrown it all into the calculator at once. Divide by 9 pi, divide by 9 pi, and we get dH dt is equal to 1 over pi, which is approximately, I did not put this into the calculator earlier, so 1 divided by pi, oops, there, hit the wrong button, is 0.318, so approximately 0.318, 309, blah, blah, blah. So step 8, our conclusion. The volume, no, not the volume, the water, the height of the water, sorry, height of the water is increasing or changing, it doesn't matter, at a rate of 1 over pi, or 0.318, feet per minute when the height is 6 feet. Okay. Now, for those of you going, how do we know that this is feet per minute? That's usually the biggest question. Is go back and look what you're putting in. So I can change my pen to red. And when I started substituting things in, this is cubic feet. So cubic feet. But this one here was feet, but it was squared. So this was feet, and if I put parentheses in there, then this became feet squared, and this is cubic feet. And when I divided, I would have had cubic feet over feet squared, and that's where you get feet per minute. So when you get done and you're like, I don't know what the rate this is going to be at, start looking through what you're plugging into the problem. Okay, so a little bit easier, maybe, I don't know. It's geometries. The things you know tend to be a little bit easier. Again, the biggest thing is forgetting your DHDT, dV, dt, dr, whatever you're looking at. Okay, so one more problem. Okay, so a trough is 15 feet long and 4 feet across the top. Its ends are isosceles triangles with height 3 feet. Water runs into the trough at a rate of 2.5 cubic feet per minute. How fast is the water level rising when it is 2 feet deep? Okay, so here you guys go. Well, let's draw it first and then we'll talk about what the equation is. So on this one, basically they're telling you that, so the ends of this trough is 3 feet, is an isosceles triangle. So you're going to draw something in with a triangle, and we'll send it down this way, send it down this way, and send it down this way. And you get a nice little cross here, and this thing is coming down this way, and then we have our angle this way. Very hard for me to draw three-dimensional, so just like it when you get it. Okay, and they're telling us that this is 15 feet across, 15 feet across. They are also giving you that across this way is 4. And then the deepest it can get is 3 feet. That's what they've given you. This is a triangular prism, so if you guys are going, how do I know it's a triangular prism? The ends are exactly the same. If they moved it up right, the top and bottom would have to be the same. That's how you know it's a prism. A box is a prism. It's a rectangular prism. The top and bottom are exactly the same. Cylinder, soda can. It's a circular prism if you want to, if they call them cylinders, because the top and bottoms are exactly the same. But this is just happens to be a triangular prism on its side. Triangular prism. It just happens to be lying on its side. So we'll take care of that. So the volume for this one here is 1/2 the base times the height times the length. So there's our function. This is not the one we're going to use, but we can assign our variables from this. So V equals volume. We don't have, we really don't need the volume, but we do need the dV dt. Is going to be 2.5 cubic feet per minute. Okay, B is going to be the base of the triangle. So in this case, your B is going to be, they told us nothing about it. They're telling us how this is, but they gave us information to use, this, this, and this. Okay, the height. H is going to be the height of the triangle. And they did say it was going to be when it's 2 feet. H equals 2 feet. So dV dt is what we're looking for. And then L is the length. And in this case, it's 15 feet. And dl dt is 0. That length is not going to change. As I put it in water, that water is going to evenly flow out in that direction. It's the base again. Just like the last problem, they did not give us enough information to do this. So I have to do that proportion of base to height, base to height. And on this thing, the base is 4 and the height is 3. So my base can be substituted in for the height of 4/3 the height. So 4/3 h. So now I don't need dB dt because this is supposed to be h. I have dH dt. So picture, we have our things in there. We assigned our variables. Step 4, assigning values to our variables. So step 3 is what function are we going to use? So V equals 1/2 base times height times length. And we need to plug in values that we can plug in. B is not a constant, 1/2 is. Base is not a constant, but we are going to put it in as 4/3 h. H is not a constant, and L is 15. We put it in now, because otherwise we'll have to use product rule, and it's a much longer process. It's one of those, if you can get it down to one variable, you're better off for it. Okay, so in the end, the equation we're going to use is 2/3. Oh, we got 15 over here. Okay, a little side work. Okay, I have 1 over 2 times 4 over 3 times 15 over 1. The 4 and the 2 cancel out, I'm left with 2. The 3 and the 15 cancel out, I'm left with 5, so I get 10. So this is going to be 10h squared. There's the equation I'm using when I do my derivative. Much nicer than having 3 variables in there. So step 5, derivative. dv dt equals 2 times 10h dh dt. Okay, so on this one here, one of the things I do want to point out to you guys that I had a feet on this one already. And when I plug, so I already had feet on here, and when I plug 10, not 10 in, the 2 in, oh, I haven't plugged it in yet. Anyways, I have feet on the, when I did all of this was already 10h squared feet. I want to point that out. So we now have, I can plug in 6 and 7, plug in and solve. dv dt is on this particular one 2.5 cubic feet per minute equals 20 times h, which is in this case 2 feet, times, and that 20 has a feet on it as well. So I'm going to go ahead and square this, because this guy had feet on it, 2 times 20, this gave me feet as well. So feet times feet gives me feet squared. dh dt. So we are at 2.5 cubic feet per minute equals 40 feet squared dh dt. I'm doing the feet, that way you guys know why it's going to be feet per minute. Divide by 40, divide by 40, feet squared. So dh dt is equal to 0.0625 feet per minute. For those of you guys going, what happened to the minute part? I just never put it in. It would just gotten in the way. So there is your DHGT. So step 8, your conclusion. The water is rising at a rate of 0.0625 feet per minute when it is 2 feet deep. There you go. And we're done. So I'm not going to say that these are easy problems. I've always had students struggling with them. But one thing that you need to be aware of is how to recognize its related rates. Beyond that, it's just a little bit of extra work. So this will probably be some of the more difficult stuff that we do. Okay, good luck on this.